Okay, so shall we start?
Wait 1 second. It's still setting up.
Okay.
Oh, good.
Okay, great. So hello, everyone. It is our great pleasure to have Dr. Xin Yung today to share his research work with us. So Dr. Xin Yung is currently an associate professor in the Department of Mechanical Engineering and affiliated faculty member of the Material Science and Engineering program at Binghamton University. He received his bachelor degree from in physics at Peking University in 2007 and a PhD in mechanical engineering from Rensselaer Polytech Institute in 2012. So after graduation, he spent 2 years in the Department of Chemical and Petroleum Engineering at the University of Pittsburgh as a postdoc associate. His research focuses on simulating and modeling a broad spectrum of transport process and the interfacial phenomena in soft matter, including colloids, polymers, and biological system. So with that, let's welcome Xin Yung to start his talk. And Xin, feel free to start on your end.
Great. So thanks, Joanne, for the kind introduction. Let me set up my little pointers just in case I need to use it. Great. So thanks everyone for joining the virtual sessions today. I know it's probably early for or late for people in the Asian, but again, welcome to the seminar sessions, and I really like to thanks the organizers for inviting me and giving me this opportunity to introduce our work to the broader community of complex fluids and soft matter community. So today I would like to talk about modeling soft matter interfaces on mesoscale. And as Joanne said, my name is Xin, and I'm at Binghamton University. So for those who maybe not heard of it, just give a quick brief introduction. So our university is one of the 4 research universities in the state of New York, State University of New York system, together with Buffalo, Stony Brook, and Albany. So we had a intermediate mechanical engineering department, but we focus a lot on small scale interfacial phenomena and fluid transport problems. So today, that's what I'm going to talk about today. So first give you a overview of what my lab has been doing in the past few years. So my lab has mainly focused on soft matter modeling across a wide spectrum of lengths and timescales, also involving various different techniques. So starting from smallest scale, we do MD simulation or MD simulations of membrane interaction with small molecules, and then we start to go up the rank or up the scale towards coarse grain MD and DPD, where we're looking at various problems involving emulsion droplet, microgels, polymer composite, thin film wetting, thin film drying, and then we also work on a little bit on lattice Boltzmann method in order to bridge the experiments where we do droplet impact, droplet drying, deposition type of stuff, as well as some of the latest development in understanding the biological flow fields generated by microswimmers. So today's focus will be largely on the mesoscale. So there are 3 particular problems that I picked in order to showcase the power of the mesoscale model, as well as to really connect with the community in terms of working on particular dissipative particle dynamics. So let me just give a brief introduction to the method that I'm gonna mainly use for this whole talk, which is dissipative particle dynamics. And I think this method itself is no stranger to most of the audience of this seminar series and the community. So this method is essentially a particle-based Lagrangian model for simulating simple and complex fluid systems at mesoscopic lengths and timescales. And you probably noticed that I steal a figure from Jen's book chapter, where very nicely summarized, the classical origin of DPD and what type of application problems it has been used for, as well as some of the more recent development and extension of the DPD for a broader range of problems. So the DPD was originally developed mainly for simulating fluidic problems as well as self-assembly, both particle and lipid self-assembly regarding basically rely connect to the Flory-Huggins theory and polymers. And then the method has been widely adopted by many groups around the world, and then start to proliferate into various different directions, including start taking care of anisotropic, asymmetric anisotropic particles, the charge effect, electrostatic, which is what I want to talk about a little bit in this talk to you, and involving the energy equation. Involving the energy equations, and then the multi-phase problems, as well as the reaction problems. So I'm not going to talk too much about all these extensions and history of DPD. So I will just only talking a little bit about fundamental of the method itself. So the DPD is essentially a coarse grain model where the representation of the materials, the fluid solid component, is by beads, by a collection of beads or groups of beads. And these coarse grain beads represent essentially a collection of actual molecules or atoms. So that's why it's coarse grain. And then the dynamics of these beads motion is very straightforward. Just follow the Newton's second law, F equal ma. And that's what we see here in this equation. And so what's important about DPD and its main difference from coarse grain MD, for example, is its force component, right? It's what forces they consider. So there are three main forces included in DPD model. There is a soft repulsion force, a soft core repulsion, which is typically used to represent the chemical specificity of the material in terms of how two components interact with each other. Do they like each other or do they hate each other? And then there are two additional forces to capture viscous dissipation as well as the random fluctuation occurring in the system. So as the right figure shows here, this soft repulsion is really what distinguishes from the coarse grain MD, where the coarse grain MD is mainly rely on like Lerner-Jones type of interaction, where you got a very strong repulsion, hardcore basically repulsion, preventing the particle from overlapping each other. Here, the soft core repulsion will actually allow the DPD beads to penetrate each other. However, that's really that also means that you can afford a much larger time step without causing any instability, as well as you can much easier capture the fluid mechanics, hydrodynamics. And speaking of hydrodynamics, the role of the viscous dissipation and random force together will thermostat the system, will provide a control to the temperature. And then you probably also notice a real characteristic of the DPD model is that all these forces are pairwise. And so this will guarantee the momentum, the total momentum of the system is conserved in our system, even with the presence of random force. And then it will allows the reproduction of the hydrodynamics property. And this has been already demonstrated by some of the early seminal papers by Espinol and others. So then that is sort of a very brief introduction of the method itself. And then for particular problems, I will add in additional description on specific component. So the first problem that I want to talk about today is about colloid polymer interface. And then the materials I'm particularly interested in is this the polymer nanocomposites. As a lot of you guys may know, the polymer nanocomposites is just simply a mixture of polymer matrix and nanoscale filler. And so, you know, just the combination of the two create a myriad of materials with different functionalities and different for different applications. So, and then the polymer nanocomposites has been play a significant role in, you know, as construction materials for drug deliveries, creating sensing, thin films, flexible electronics, and coatings, and etc. So it has a great applications, but there are still a lot of fundamental questions that have not been addressed fully in this field. So in particular, what we are interested in is control microstructure, because as we know, the function of the material itself is closely tied with its microstructure, as well as the processing process, right? So there is a you know, a so-called structure structure processing or processing structure property relationship. And so in order to understand this structure formation, so there has been extensive work looking at the particle side. So people have varied the size of the particle, or in filler, the concentration of the particle as well as the shape. However, much less work has been done on the polymer side. The reason is because it's typically much easier to control the particle filler instead of varying the whole polymer matrix. And so in particular, the effect of molecular architecture of the polymer as well as the chain conformations on the entire evolution of the microstructure has not been like fully studied. So we got this motivated to work on this problem by essentially a problem provide to us from our experimental collaborators at Iowa State. So Professor Shanjiang's group at Iowa State work on the bio-based polymer composites thin films, where they look at adding in zinc oxide nanoparticles to these bio-based bio-based polymers, the 2-hydroxyethyl starch as well as 2-hydroxyethyl cellulose. And then they want to use this for creating UV protection coatings. So one important interesting finding they found is that despite the similarity of these two polymers, as we can see here from their chemical structure, they are essentially similar polymer, same polymers in terms of chemical wise. Despite the only difference is that their position of the hydroxyl groups are different. That will lead to different conformations and their bulk properties being very different. So starch is more like amorphous polymer, while the cellulose has more ordered and more sort of polymer itself is more stiff. So what's interesting is that they find out that by adding in the zinc oxide to these two polymers with very similar, basically with the same chemical constituent part, the particle structures are completely different. In HES, where they observe this zinc oxide is basically form these isolated particle clusters, as you can see from this SEM image, while in HEC, these particles certainly sort of assemble into large percolated networks, as you can see here. So you got these mesostructures. And so that really inspired us to looking at, okay, because these two polymers are so similar to each other, the only difference really is their chain conformation, where one is soft, one is stiff. And so we want to looking at how the chain conformation specifically influence the particle assembly in these type of systems using the DPD simulation. So in order to model DPD, model polymers and nanoparticles in DPD, we adopt very basic, simple models for the polymers. So we just use a simple B-spring model with harmonic bound potential and cosine angle potential. So these two will controls the connectivity. The bound potential controls the connectivity, while the angle potential tunes the rigidity of the chain. So by simply increasing K, we could vary the polymer conformation from a global, coil type of polymer to a very stiff chain. And so the K can be also relates to the persistent length of the chain, which give us more, physical relations between a simulation parameter and then a physical parameter of a physical property of the chain. Now, in order for to model nanoparticles, we just simply introduce them as rigid clusters of solid beads putting together. So the only a little bit special thing here, what we're doing for a spherical nanoparticle is we create these particles by superimpose a face-centered cubic lattice core, as you can see here on the right, with a surface layer that the beads are uniformly placed on a spherical surface. So the reason for doing this is that basically we cover this core with this surface layer in order to achieve high rotational symmetry. Because otherwise the core will be more like a polyhedron instead of a spherical shape. And so we put together the polymers, and then we put together the particles. So here the red ones are the green chains are the polymer, and then the blue spheres are particles. And then more importantly, because in the experiment, the films are formed by drying, right, by evaporation. So we do consider the presence of solvent. So in all these cases, we first consider the equilibration of these multi-component systems with 50% of solvent, which are not shown here. I will show it later. And then we vary the rigidity of the polymer, and we try to look at how the particle assemble themselves. So these are two videos that for very soft polymer and very rigid polymer that we see here. So one thing you can notice very clearly is that for soft polymers, the particles are pretty much just randomly dispersed in the matrix. However, when the rigidity increases, the polymer itself start to form the nematic ordering, and then the particles will try to expel out from the polymer region. So in all these states, we consider the polymer to be well dispersed in the solvent, so they like each other with neutral interactions. And then the polymer and particles are slightly dislike each other, so they can still be randomly dispersed. But when the polymers density are too high, the particle will be expelled out. So what we see here is the rigidity of the polymer will actually influence its assembly, so that it's not inhomogeneous. It's not homogeneous anymore. You have some kind of microphase separation, and then the particles start to only be sitting in those voids. And when we characterize the nematic ordering parameters for the polymer systems, as we can see here, by varying the K, we first you don't see much of change. So that means the system are highly homogeneous and random. And as you start to increase this over 30, you start to see the development of the nematic ordering. And then this gets increasing in time as well as increasing in K. So then we're looking at the particle inside this system. What's their diffusion? What's their dynamics? So we quantify the mean square displacement of these particles, and then we find out in general, in long-time scale or on long-time scale, the particle diffuse normally, so it dynamically exhibits normal diffusion. And so we can extract the diffusion constant or diffusion coefficient by fitting the MSD on the long time scale. And so this plots demonstrate the variation of the diffusion coefficient as a function of the rigidity of the polymer. So one interesting observation here is that this variation is non-monotonic, right, which might be a little bit confusing. So we see that when we start to increase the polymer rigidity, the diffusivity first reduce. That means the polymer start to more suppress the diffusion, and then the particles are more sort of caged in the matrix. However, when the nematic order regions start to develop, we observe the constant increase of the coefficient. And so what that indicates is that the particles start to get more freely to diffuse when there is microphase separation. And then that's because this creates the a solvent rich region, and then that will facilitate the diffusion of the particle. Now, speak of the interaction, speak of the assembly structure. Let's look at what happens when we introduce solvent evaporation. So here we just model the evaporation very simply by just taking out the solvent beads gradually in time. As you can see here, now we do plot solvent, which are these dark blue dots. And so as we start to evaporate with this highly rigid system, we see that the particles start to aggregate and start to form clusters. And of course, because the space where it resides in is shrinked as the evaporation of the solvent continues. So by looking at the particle structure alone, we can actually observe a very interesting transition. Again, it's very non-monotonic. First of all, we're at the for very soft chain, the particle will ultimately form isolated clusters, but these clusters are more isotropic. So we do not see any preference in terms of the elongation. And then due to the lack of diffusion or due to the suppressed diffusion, the particle becomes more well dispersed in the matrix at in the final structure as at this intermediate rigidity. And then as we further increase rigidity, the particles start to aggregate again. However, this time the aggregation appears to be very anisotropic. And this is because we believe this is the polymer ordering and the orientation of this nematic region guides the aggregation of the particle, as you can see here. So so this more isotropic cluster versus a very anisotropic elongated cluster. So then we further quantify the assembly structure by calculating the relative shape anisotropy, weighted or averaged relative shape anisotropy of the entire system for multiple clusters. So here the relative shape of each cluster will represent its general geometry, and then we calculate average by their weight, which is the number of particles included in this particular cluster over the entire particle. And then we can see this anisotropic relation is also non-monotonic with a minimal around 20, which is in agree with our particle diffusion. And then the connectivity, which is counted by the number of linked particle over the total particle, will also exhibit a similar behavior. But in time, as the evaporation goes, we always see a monotonic increase in connectivity, which makes sense because it basically squeezes the particles together. And then, so that sort of demonstrates the plane chain, right? For how its rigidity influence the system. Now, in reality, many of these chains, for example, the 2-hydroxy acyl cellulose, they do have side chains, right? Their side chain is actually the ones that the modification that prevent them to be fully crystalline. in contrast to the original, the pristine cellulose. So in this case, we also explore the effect of side chains. So here we are adding a soft side chains to the primary chain, to the backbone, where we adding them from a distribution of lengths and then randomly along the backbone. And then, so we do vary their concentration in terms of how many chains they have along the backbone. And that's represented by this percentage. And then we see here is the general trend is very clear, which is the introducing of sidechain reduced polymer ordering, because now they have to overcome much higher entropic effect to make them ordered, right? Like to develop the nematic order. So we see that it overall disrupts the polymer ordering and then also reduce the particle assembly structure. So everything gets more well dispersed. And so the quantification of the particle structure also confirms this. And so finally, we would like to compare our simulation to experiments. And so in order to compare our simulation, we run a much bigger system. You probably can notice here, this system is much bigger than the ones that I demonstrated before, because we want to see whether these elongated aggregates will ultimately connect it together to form percolated networks. And so our result shows that in general, it qualitatively agrees well with experiments, where these elongated clusters after evaporation, they're gonna come close together and then start to form percolated networks. While for the soft polymer matrix, the particles are just isolated, more isotropic clusters. And then our experiments demonstrate that this behavior is very consistent for different particle fillers. So we try zinc oxide dispersion, zinc oxide nanopowders, titanium oxide, dioxide nanopowders, silica particles. They all demonstrate very consistent mesostructures in HEC matrix, and then also isolated particle aggregates in the HES matrix. So this behavior is certainly not dependent on specific interaction between particle and polymer matrix, which supports our explanation that this is due to a physical effect that's generated by the chain conformation, which is more like an entropic. So to summarize this part of the talk, so we demonstrated using Mdbd how does polymer conformation influence the particle behavior in the mixture. So we see that the conformation not only influences the dispersion state, which means that it will controls whether the particles are dispersed or aggregated. It also changes the morphology of the assembly. So we demonstrate both globular as well as fractal type of assembly. And then the fundamental mechanism of this structure formation is because the polymer start to develop nematic order, and then they actually cluster themselves in the presence of solvent first. And this create local solvent-rich voids that will guide the anisotropic particle aggregates. And then this hosting, the presence of these anisotropic aggregates will percolate it into mesoscale structures upon solvent evaporation. And then we also developed the interesting non-monotonic particle dynamics due to the change in terms of particle and polymer coupling, the coupling of their dynamics. So now I would like to change gears a little bit to look at the colloid interface. And then the system which we're particularly interested in is microgel. So microgel is basically cross-linked polymer particles of size, from 10 to 1,000 nanometer. And these microgel has found significant applications in drug deliveries, emulsion stabilizations, and novel assemblies, sort of creating novel assembly structures. So these microgel are typically thermal responsive, so responsive to temperature variations. And so the previous work that focused on the particle interactions, the interactions of these microgels has been very limited to a specific temperature range and structure. And so they, in particular, they mainly focus on these particles, these microgels in a swollen state at low temperature. And so they want to develop a theoretical interaction so that they can extend this interaction to understand their assembly as well as the rheology of the microgel suspension. But as I mentioned, the current model is very limited. In particular, they do not consider that the microgel itself varies a lot in a wide range of temperature and with different cross-linking density. So our aim is to looking at this problem, again using Mdbd, but try to looking at how temperature influence the interaction and try to come up with a theoretical model for describing these interactions in a wider range of temperature and structures, the particle structure. So first of all, we want to create microgels in the simulation. So here we use our previously developed in silico emulsion polymerization technique to create the microgel. So basically here we actually model the polymerization in the presence of 55% cross-linkers within a droplet, within an emulsion droplet. And then this method allows us to create a microgel with more realistic network structure. In particular, is inhomogeneous core shell structure. And then we can parameterize our system, our Mdbd, to capture the temperature dependence. And this has also been we utilize our previous knowledge working on this type of hydrogel system. So as you can see here, we can capture these phase transitions where the microgel shrinks as temperature increases, and then the transition temperature corresponds well with the experimental observation. So this system is particularly representing a polydiapone. And then once we have these particles or this microgel, we start to quantify, characterize their interaction. We use steered Md simulations to introduce their interactions or to let them interact with each other. So basically, the steered Md, the concept is very simple. We add an external spring to the center of mass of two microgels, and we pull them together. Okay, and so the reason of doing this is that it will facilitate their interaction, and then also it will provide ways to quantify their energy, as we're gonna demonstrate in a minute. So the interesting observation we see here is that at low temperature, when these microgel are swollen and fluffy, they basically just pure repulsion. As you can see here, when they come close, they deform, and they really don't like to interact with each other. On the other hand, when temperature increases, we start to observe a very characteristic neck formation or bridge formation, which is reminiscent of the droplet coalescence. And that indicates these particles are very adhesive to each other, and the surface tensions start to play a role, which allow them to spontaneously interact. And so we could quantify the interaction energy by calculating the potential mean force from the steered Md, which we utilize the Jasinski equality, which calculates the work done by this spring which pulls these two microgels together. And so this is the original data, which is the work, and then we can obtain the PMF from its essentially statistical variation. And so this is the obtained PMF. As we can see here, what's interestingly I want to demonstrate is that as temperature increases, the interaction with this quantifies the free energy profile of two interacting microgels. They change from pure repulsion to attraction, to exhibit the attraction well. So in a regions where they overlap or based on their distance, there is an attractive well. So that's a very important observation we see here. And so we try to come up with theoretical model to describe this this potential that calculated in the simulation. So we kind of combines you know, the two important contributions to this interaction, which one is the elastic contribution, which is due to the deformation of the spherical microgel, and then that should be pure repulsion. And then there is surface tension contribution, which is due to the surface tension, interfacial tension between the microgel and then the solvent, which when the microgel is swollen, I'm sorry, when the microgel is collapsed, that surface tension is higher. So in this case, we developed the interfacial thermodynamics calculation by looking at the surface free energy change. And this basically depends on the temperature-dependent surface tension multiplied by the area change, which due to the merging. So the total potential is unified basically from these two contributions. And so we theoretically derive this. The surface tension will also depending on the temperature. So we would put in our previous developed chi parameter for these hydrogels into the model. And so the two fitting parameters are only this n for describing the soft repulsion, and then this epsilon, which is also the strength of the soft repulsion. So we can, as we can see here, the theory fits very well to the simulation data. And so we also capture this dependence in temperature. And so we also looking at if we what happens if we vary the cross-linker density of the gel. So here we explore different densities. So the three, as we gradually increase the cross-linker density of the microgel, the microgel becomes more rigid, and so the elastic contribution start to overcome or become more dominant. And this can be evidenced from the difference between the two temperature curves gets smaller and smaller, as you can see here. The gap, you know, and then the attraction region, the attraction well gets shallower as the cross-linker density increases. And so we're further looking at the detailed dynamics of the necking because we found this very interesting. As this microgel, which is considered to be more like a solid particle, although like deformable, they demonstrate you know, traits of droplet or liquid droplet. So we quantify we're looking at the dynamics more carefully. So here we put the microgels very close to each other, and then we don't apply any strain. So because we want them to interact naturally. And so we observe that the neck forms between these attractive microgels in the collapsed state. However, the evolution is highly arrested. And then at the end of the day, we got a dumbbell morphology. And so this behavior is, you know, we try to compare this with Newtonian droplet. And there has been a lot of recent studies on the nature of Newtonian droplet coalescence, in particular their initial dynamics. And then we also want to compare this with viscoelastic polymer droplets, because we believe this microgel certainly made of polymer carries a lot of characteristic of viscoelastic materials. So we see that this you know, arrested evolution is very similar to what they see in the you know, in viscoelastic droplet coalescence. So we try to but nobody have ever characterized the detailed dynamics of this neck growth for microgels. So that's what we try to do here using DPD. So this is a comparison between three different cases: a pure liquid droplet, a polymer droplet with a short chain polymer droplet, and then a microgel. So as we can see here, it's surprisingly that these three cases exhibit very similar dynamics at early time, where they all demonstrate or they all show a characteristic linear growth, which is reminiscent of which resembles more like a Newtonian system, Newtonian fluids. However, as the in a long time scale, it's obviously that they behave very differently. So for microgel, the neck growth is very arrested, and then they basically flatten down. And so this final morphology is also very different. For liquid and polymer, they will finally merge and completely mixed with each other, while microgel just form dumbbells. And so we're also looking at the effect of network elasticity by changing the cross-linker density of the microgel. And we can see here, this doesn't change the initial dynamics. The late dynamics very clearly changed due to the variation of elasticity. So the final steady state neck radius is much smaller when you increase the cross-linker density. And so we try to, because of the initial stage is much better understood, we want to understand more of the late stage, where apparently the elasticity and viscoelasticity play the role here. So we developed an analytical model to try to describe this neck evolution in this late region. So we start with describing the particle movement in the 1D, where we described the two particles moving close together under the friction and then their particle attraction. So here, this is a full 1D Lagrangian equation. However, we can drop the friction because the random force, because the random fluctuation is typically much less than other component. And then we will consider overdamped system, because this is everything is immersed in fluids, right? So it should be the radial number should be very small. So the inertia is limited. So we only consider friction and balanced by the particle interaction. And then a trick we do here is we can recast this equation in terms of neck radius by relating the velocity of the particle movement along the axial to the neck growth. So this is due to this is considered by the flow incompressibility, where there's a relation developed by Poisson that relates these two velocities together. So these two velocities are orthogonal to each other, but there's a relation between them. So we can now recast this particle equation using the radius variation, the neck radius change. And so we can see here, this radius change will be balanced by two contributions. One is the elastic resistance. So here is this sigma is the strain, the stress in the neck region, and then the surface tension. And then we can further work on some mathematics here by making several assumptions. First of all, consider frictions are concentrated in the neck region. Therefore, it's proportional to the size of the neck. And then we also assume the change of this is relatively small, so it's a linear elastic regime where we consider the strain is constant. And so then the whole neck equation will become basically balanced by the dynamic elastic modulus and then a surface tension contribution. And then from the presence of the final steady state neck, we can know that these two contributions will ultimately balance each other, because that's how you get zero, right? You get zero variation in the radius. So we argue that the total modulus, elastic modulus, is contributed by a visco elastic contribution of the polymer chain in the neck region, and then a whole elastic contribution from the deformation of the total network of the microgel. And so the total network, and then in the steady state, the total network contribution and then the surface tension cancels each other. And so therefore, we can also assume quasi-steady state where they will cancel each other in all times. So therefore, the neck change will be only governed by essentially the viscoelastic contribution. And so using a Maxwell model, we can obtain a very simple exponential relation, where here the only two fitting parameters are this B and then this characteristic relaxation time of the chain. So by fitting this system to our simulation data, we can obtain these characteristics, the quantities. As we can see here, as we increase the cross-linker density, we reduce the relaxation, and this is because the polymer gets shorter, right? And so this is also the trend is qualitatively consistent with Rouse model. Of course, this is a network. So the real relaxation is much more complicated than Ross model, but the overall behavior is consistent. More importantly, by using this theory, we can now collapse all our simulation curves onto one master curve, as we can see here. And so then there are two regions which characterized by this master curve. One is a viscous linear region, and then a viscoelastic curve. And so the intersection of these two lines will determine a crossover characteristic time, which dictate this visco to viscoelastic crossover. And this is the first time that had been reported these particular transitions between two regimes. And so I want to quickly summarize this so that I have time to talk a little bit about the DPD with electrostatic interactions. So basically, we're looking at that the microgels behave very differently as a function of temperature in terms of their interaction. And more importantly, when they are in collapsed state, they exhibit capillary dominated attraction. And so we can model that very basically based on the interfacial thermodynamics, using a very simple toy model. And then we also see that the gross dynamics of the neck exhibits a novel crossover from the viscous to viscoelastic regime. And then in the long time regime, the viscoelastic growth is only governed by the polymer relaxation in the neck, which is intrinsic, which is relatively counterintuitive. And so now I would like to switch gears again to talk about interface between multi-complex fluids droplet. So the motivation is to looking at the electrospray deposition, where the high voltage is used to generate these fine droplet, which carries the materials to a substrate. And so it's for deposition and surface patterning and various surface applications. So our question is, we want to looking at the deposition of the polymers, but when we look into the literatures, we only find these major dominant morphology. It's either create individual particles or electrospinning a wire mat where all these continuous lines, fibers lay on each other, or sometimes they can get films if the solvent is not completely dry. So everything gets, you get the dewetting behavior. So we're thinking about this. There should be a natural regime between the particle and then a long wire or non-continuous wire, which is a short nanowire that due to the deformation of the individual droplet, so it's not connected. And then from the literature, we find that this state is missing. And so we try to identify, okay, why that's the case, and is there any way that we can create these particular novel structures in electrospray? And so we try to explore the in-air self-assembly and morphological evolution of the multi-phase droplet in ESD. So this droplet is going to be electrified. So the hypothesis is that typically you only form these anisotropic beads on strain structures, because when your evaporation happens, you're going to get a density gradient, which translates to a viscosity gradient. And so you got a liquid core and then a dense shell. And so this liquid core going to migrate faster under the electrohydrodynamic deformation. So that will lead to this this string formation attached to a center mass. Now, what happens if we can potentially create a droplet that have a very homogeneous viscosity increase upon the time of deformation? And so that should give us a uniform nanowire, because that deformation gonna now carry it out on the entire droplet. So we try to explore this hypothesis from using DPD. So here I'm gonna add another ingredient to the DPD, which is the electrostatic. So we adopt a very basic model, which is developed by Groot. And so solving electric field due to the charge distribution, the Poisson equation. And so what's important here is that this method we're picking is able to account for the dielectric contrast through this local polarizability parameter. And this Poisson equation needs to be the charge needs to be distributed in DPD to avoid overlapping of the collapse of the ions under the soft potential. And so we distributed using basic linear distribution. And so from the distributed charge, we can back out the force if we can solve the potential on the grid. And so the Poisson equation is solved using our in-house code in real space using parallel SR successive over-relaxation method. And then that's how we get the electrostatic into our system. Now to model evaporation, we do it phenomenologically. So here we have vapor beads representing, essentially we're doing a two-phase flow. We have vapor beads outside, and then the internal is droplet with ions, polymers. And so we evaporate, or we basically remove the water, the water beads only near the surface of the droplet. But then to maintain the constant density of the Mdbd requirement, we'll add back solvent beads to the exterior region. And so this will allow us to mimic the physical droplet evaporation subject to the D2 law. So as we can see here. And so then when we apply this, as the droplet shrinks, the charge gets concentrated, and then they will start to deform the particle and the polymer. And so we see that when we carry out the physical evaporation, we observe a very typical bead-on-string structure with central mass and then a filament attached to it. Now we confirm that our density is non-homogeneous by looking at the polymer density distribution, where we see that we remove the beads at different rate, but overall with these ranges, we see a very clear polymer shell and indicated by this density distribution. So this confirms the skin formation. And so the bead on string is very robust in these regions with these rates. Now we want to test our hypothesis. What if the viscosity transition is homogeneous? So here we model this gelation. So we believe that the gelation will help that. So we model the gelation by, instead of evaporating the solvent, we just homogeneously remove it throughout the entire droplet. So in this case, the polymer concentration will be homogeneous throughout the whole droplet. And now we see the characteristic deformation is very different, where the pseudopole still forms, but then the deformation will now involve the entire droplet and elongate it. So we get a nanowire structure, okay? And then we further confirm this, that if we really evaporate this extremely slowly, like compared to in our simulation setup, we can reproduce the same nanowire formation under the homogeneous removal of the beads, and then the result shows similarly. Right? We still get the similar deformation, and then the polymer density confirms that the chains are distributed homogeneously within the droplet, so that we should expect the viscosity being the same, being uniform. And so we realized this experiment by our collaborators at Rutgers, who find out this particular material, mesocellulose, in a water ethanol mixture. If we spray it, we can lead to this gelation where obtain this nanowire forest. So these then forms. So these are higher order three-dimensional structure of the individual nanowires that we see similarly in our simulation prediction. And so we still do not fully understand what's the formation mechanism here for this rapid homogeneous viscosity increase, but we believe it's due to the enhanced fibrillar gelation under the extreme shear and surface charge. So effectively, the individual droplet electrospins. So you can think of that way under these conditions. And so I'm pretty much used up my time, so I'm going to quickly flash through some of these additional new development that we're doing here. So we're further looking into the influence of particle feelers. So here we're just adding in different particle of different sizes to the droplet and try to observe its influence on the morphological evolution. So it's very clear that when the particle is large, it can arrest and suppress the deformation. And this can be characterized by the relative shape anisotropy, and then the radius of gyration. And so we also realized this by spray mesocellular silica composite spray. So as you can see here, we observe very similar tiny filament if the particles are very large. So it basically occupies the entire droplet's volume. But then for small droplets, they can be well dispersed in the small nanowire. And then what happens if we introduce multiple particles that have very small size? So in this case, the solid fraction is increased, but they are fairly homogeneous compared to individual big droplets, big particles. And so we see here that this we can also suppress the deformation when the solid fraction is high, but when the solid fraction is low, we observe a more robust wire formation, the nanowire formation. So if you directly compare a multi with single, you can see that there are some subtle changes between these two dynamics. So the single case is less homogeneous, and you get more like a tadpole shape, while for multi one, because the viscosity modification or viscosity change is much more homogeneous, you get a better nanowire formation. And so we can also characterize the morphology which is consistent with our experiment simulation prediction in the experiment. And finally, we tried like fillers with exotic shapes. And so one interesting observation that we just found is that we find nanowires pretty much always form from the edges and vertex of these particles, which we believe is due to this curvature that enhances the local electrical stress, which facilitates the wire formation at the local point. So I guess I'll skip the summary. I'll leave the stuff there, and I'll quickly just acknowledge the students working on these projects and my two collaborators, Professor Shen Zhang and Professor Jonathan Singer, on these projects, and as well as funding agency. And finally, I would like to thank you for your attention, and I'm happy to take any questions.
Yeah, thanks, Xin, for the very interesting talk. So if there is any question from the audience, please feel free to unmute yourself and ask your question.
Xin, I have thanks very the wonderful talk. Actually, I enjoy a lot when you divide the theoretical analysis part to explain what happened in the simulation. So
yeah, I mean there's a lot of details I could probably put too much stuff here, but yeah, I will just showcase them so that if you have any questions, we can discuss offline.
Yeah, so for the second part, you use the cross-linker, the density of cross-linker to control the elasticity of the gel.
Yes.
I'm not sure if there's a linear relationship between the cross-linker density and the elasticity. I suppose this is so when you set up the cross-linker, you kind of randomly select the cross-linker position, right?
That's a great question. So this goes back to yeah, I didn't get a chance to elaborate on how we actually make these microgels. I mean, I mentioned a little bit, but I think it's probably just too quick. Let me just go back to the. So, as you said, the way we generate this microgel is a little bit different from some other approach, because like old approach is that you create like a network, like a regular network structure with constant polymer strand length, and then you define you basically link them, right? Say you can use a diamond lattice structure or some other structure or cubic lattice structure, and then you just put the cross-linker at the lattice points, and then you make the chains between them. So that's a very common way of making microgels. But here we adopt a different one. We literally, as you said, we first initialize equilibrate a droplet, which is a mixture of monomer and cross-linker and initiator. So initiator, monomer, cross-linkers, and solvent. And then we have an in situ or in silica reaction which connects these beads together. And so therefore, the cross-linkers are random. Yeah, they are randomized. And then the structure is also highly inhomogeneous. But we believe this will represent better the experimental condition, because in experiments, how you create this microgel is really just making them like polymerize in a droplet, in the emulsion droplet. So the concentration only influence how many cross-linker beads we put into the system, which will in turn influence the average strand length, but it does not guarantee. I mean, it's the network itself is inhomogeneous.
So have you tested the rigidity or elasticity of the microgel?
Yeah, that's a great question. We didn't directly test the mechanical property, but from both these potentials, interaction potentials, as well as not this one, the right one. From these interaction potentials, as you can see here, there's a significant change in terms of the repulsion region, as well as the neck growth. Where is that? Here. This will reflect the change in the elastic property of the network itself. But in short, like we didn't get a chance to really measure like what is G prime and what is G double prime.
Okay. I have another question. In your first part, when you consider the nanoparticle and the polymer self-assembling process, so I noticed that the nanoparticle is there's a lot of nanoparticles. So when you consider the nanoparticle, do you use a rigid body?
Yeah, that's an excellent question. Yes, in short, I believe it's so these simulations were carried out in labs, and I believe these was used for. I probably used rigid bodies, rigid small. So it's a bunch of small rigid bodies which are accelerated. So they are. So it's a little bit hard to see here, but each particle is about, I think, around 100 beads, sort of. And then there are, I think, around 100, a little bit more than 100 of them there. So
okay.
These simulations are pretty expensive.
Okay.
But they are rigid body, yes. But then we were discussing lubrication. Now, just to clarify that, there's no real lubrication here. So there is solvent, but there's no lubrication reaction here. Like we're not adding anything. This is a very standard like Dbd system.
Okay. So if we need to consider this near surface interaction, actually maybe we can use bonded particle, right? Bonded particle maybe is another option to simulate.
Yeah, right. But I mean, in general, as a lot of you, the audience probably also know that incorporating lubrication in Dbd framework is not trivial. I mean, it's certainly not trivial. The issue is the Dbd allows certain degree of overlapping and penetration, right? So, and even incorporating nanoparticles, I don't think there's a golden standard in terms of how do you pick the density of the particle, for example, like in terms of the piece density. So, and then how do you treat the boundary conditions? I think Professor Jenny has probably more expert, can say more about that in terms of how to treat boundary conditions. Anyway.
Yeah. Okay, thank you.
Yeah.
Okay, so any other questions? So in fact, I do have a question about this page. So since we are here already, so not only about this page, I noticed that for almost all examples that you have shown in this talk are for the complex system, right?
Yes.
So I'm just curious how you calibrate the interaction. Say,
that's a great question. I mean, that's a great question. I mean, I think anyone who's who cares about modeling probably would ask that question. So the interaction stuff, yes. So typically, it depends on different things. For microgel, so microgel system is one that we had better calibration. So I will maybe use that as the example. Let me just skip to there. Okay, yeah. Okay. So we have done this actually in the past. So when we work on this hydrogel, we do rigorously consider the chi parameter, and then this chi parameter is parameterized against experimental data in terms of its temperature dependency, and then we convert the chi parameter to the DBD parameter. Now, I know there's a lot of debates on the degree of cross screening, and it's dependent on the DBD parameters. So here we're still doing things in a fairly traditional way, where we just consider 25 sin, like for density of 3. And but what we're trying to do here is we try to, especially for these gels, we try to we measure the collective degree, collective diffusion of the chain within the gel, and then we match that to the experiments. And then we making sure, I apologize, I do not have a figure showing the phase transition. We have calibrated very carefully the phase transition curve in terms of the polymer density as a function of the temperature, and we match the swollen densities and collapse density as well as the transition temperature. So that's one of the example how we typically characterize that. And then the units, the simulation units, it relates to those several physical quantities to determine the mapping between the DBD units and the physical units. Now, go back to the other systems. Most of the time we rely on experimental information, experimental insight. For example, in that particle, in this system, we know that the two polymers are very well dispersed in solvent, which is water, aqueous solvent. And so we basically that's how we set up our basis. We just consider the polymer solvent to be neutral. And then we do know from experiment that the zinc oxide is weakly incompatible with polymer. And so in that case, we just pick a reasonable number, say, I believe we picked 35 here, so which is not leads to strong phase separation, but weak phase separation. But in these cases, we do not have a particular chi parameter that, or perhaps particular surface chemistry that we can directly map to. But whenever we have something that we will try to have in the chi parameter, especially for the gel case.
Say for the for example, for your particle, so particle is rigid, it's okay, but for your like long chain like a polymer,
Yeah.
so that polymer can exactly follow the DPD governing equation. Then the interaction, right. So you do did you use the Lagrangian type like interaction, or
no? That's what I'm saying. So this is traditional DPD, which
just a traditional.
Yeah, the conventional the convention for no, I'm sorry, the conservation force. The conservative force is soft core.
Okay, so if you follow the traditional DPD formulation, then you may have several like parameters to calibrate, but the conservative force, the parameter for the conservative force might be more important.
Yeah, that's only one. Yeah, it's typically just that the repulsion strength. That's
also the cutoff, right? The cutoff radius.
But that only for the standard DBD. If you're talking about, say, many-body DBD, then you're going to involve more, right? And then if you want to do other EOS systems, then you're going to have way more parameters to calibrate. And and also one other thing is sometimes we do. Oh, by the way, we sometimes calibrate we sometimes select the interaction parameter by the physical property. For example, surface tension. So if you do like a droplet system, you could map the surface tension.
I see. Thank you very much for the further question. I think there are some other questions from the audience.
Oh, sure.
Hi.
Yeah.
Hello.
Yeah.
Hi. Okay, let me first introduce myself. My name is Jibao Lu. I'm from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. And I got this link from Professor Li Zhen, the sharing link.
Yeah.
And it's my I'm so glad that I joined this seminar, and thank you, Professor Yong, for the interesting presentation. So I have a couple of questions about the first part of the work that we have been discussing just now. So what's the diameter of the particle, and in the real units? And what about the cone length of the polymer of the polymer matrix as well as the
right? That's a great question. So for particle size, I don't have it on top of my mind immediately, but I believe, let's talk about simulation units first. So the particle radius should be somewhere around 1.5, around that. And then the polymer length is 150. And then the persistent length, you can calculate it based on this relation, which we use B equal to 0.5, I believe. So K is varying from 2 to 50. So the cone length is varied. It's gonna be somewhere around, let me see, from 1 to 20, something like that. So for very rigid polymer, it's pretty much like, it's pretty much like a rod, like a bendable rod. So and then in terms of physical units, for this particular problem, I can't recall whether we map it to the physical units. We probably didn't. So I will speak of the experiment system that we're talking about. The particles are 15, I think 50 nanometer or something, or 30 nanometer. 30 nanometer. The particles are 30 nanometer. Now in the real experiments, the polymer, I think we did characterize the size of the polymer. I can't recall top of my mind. The persistent length of the HEC is 6, and then the persistent length is 40. So for HEC. Now the polymer itself is much longer for sure. But that I believe we pick the ratio of the persistent length to the particle size to guide us picking the particle size in the simulation. That ratio is the one that we really change actually. Okay,
that makes sense. So it looks like the polymer crystallized.
Exactly. Yes. Polymer. I don't want to use the full crystallization because these the polymers are like locally, so you don't get like you don't get like a whole thing. It doesn't grow indefinitely. So it forms local clusters that has very strong nematic order.
Okay. So what's the ratio of the consistence length of the polymer with respect to the particle's diameter?
So this varies. For HEC, it's small. It's less than particle diameter, and then for HEC is I think in our simulation it's much longer than the particle diameter, but in real in the experiments, as you see here, it's about 1.3.
Okay. So the okay. So have you ever characterized the viscosity of the composite? So I know you.
That's a great question. Unfortunately, the answer is no. The reason is characterizing viscosity for this system is actually quite expensive because I mean, the typical way is using Least Edwards. So you have to share the box, and then you have to measure the G prime, G double prime. We can do that, but I don't think we did that at that time because I think a lot of things that we believe that seen here are mainly equilibrium phenomena, where where the viscosity is more like a non-equilibrium, associated with non-equilibrium behavior.
Okay, I understand. Yeah, probably you have to do like 200 simulations to get the ensemble average.
Yeah, and also one note I do want to mention here is, I believe when you share it, the polymer gonna develop ordering by itself just by sharing. So that's a completely different thing, because then you're gonna involving an interplay between a shear induced ordering and then a rigidity entropic induced ordering, basically.
Okay, yeah. What I have been thinking about is probably the ratio of the persistence length of the polymer and the diameter of the particle
Yes,
maybe matter.
that makes, yeah, that's definitely play a very important role. Yes, because that's gonna effectively, basically from the particle point of view, it will tell how soft the particle. I'm sorry.
How soft? Yeah, exactly. Yes. Okay. Thank you so much.
Yeah, no problem.
Yeah, any other question?
Hi, Joanne. I have a question.
Yeah.
Oh, hey, Tang.
Hi, Xin. Hi, nice to see you online. So, I'm from Syracuse. I think we have some communication before. That's a very nice talk. I want to follow up about your discussion with Jen about the boundary condition. I know that there are many different options for setting up the boundary condition. As you mentioned, Jen may have some other method maybe more rigorous. And for your current simulation, how basically it's not a question, but maybe ask your suggestion. What's your general suggestion guideline of choosing the boundary condition in DBD and Mdbd between liquid and solid?
My general experience on that aspect is if we're talking about particle boundaries, like real complex non-planar boundaries, solid, like non-planar solid liquid boundaries, it's very hard. I mean, I can't even come up in my mind of like a method which can really rigorously handle the no-slip boundaries on a big particle, or not big, I mean not necessarily big, but on actually a particle sort of embedded or immersed in a DBD liquid. Now, most of those boundary conditions, I assume you're referring to, they are for system boundaries. Like if you want to simulate channel flows, I mean there are like a lot of good boundary conditions which make sure you got no slip, you got like right flow profile, etc., and you don't have penetration. You don't have weird like density density fluctuations. But for particle, I guess Jen, maybe if you want to comment on that. I at least to my knowledge, I can't really thinking of like a efficient way, because a challenge here is if you want to do particle is moving, right? So you have to track that boundary like in time, and it's typically it's also typically curved, right? That's really like problematic for numerically.
Probably more specific, like your current system, you have this spherical, like a larger particle,
Right.
and
Yeah.
your DPD,
Right.
and like what boundary condition you think
Okay,
is
yeah,
enough?
that's a good point. So the particle that we calibrate here is largely just based on the density. So the method I'm picking the density of the surface layer and then the density of the internal is first to prevent solvent penetration. So when you plot the solvent density as a function of distance from the center, you shouldn't see anything within the layer, basically. And then to minimize the fluctuation as much as possible out externally. And so in short, I can tell you, I believe laterally, I believe tangentially, it's definitely not no slip. So that, just to put that straightforward, I think that's definitely not no slip, because there's no restriction on that, unless you adding in like friction type of force, like rotational type of force, you cannot prevent that. So the boundary condition in here will be like I would consider, we didn't measure it, but I think it's more like a no penetration plus like a small slip.
Okay, I see. Yeah, I have another question. I think you mentioned DPD is soft, and also like compared to other coarse grained have some advantage. I think DPD, there is a fluctuation there. I think people mostly always set the temperature equal to 1, and there's some like a fluctuation relationship. Currently, I'm interested in applying DPD to a larger system. It's like for larger system, the dissipation may be smaller. And one simple thing is I can think is I can reduce the temperature from 1 to 0.1 or other smaller value. Maybe I can also scale down other force parameter. But do you think it's a good way to change the thermal fluctuation in the DBD system, or do you have other suggestions?
Yeah, I mean, I think one important thing I forgot to mention here is I'm mainly like I want to admit that I'm mainly a user of DBD. I don't do like really like hardcore development, which I believe like Jen did. So speak of the fluctuation, I think the key merit of DBD is its ability to capture the fluctuation and then reproduce hydrodynamics. If you are talking about the system that you don't actually need fluctuation, I mean you're basically if you tune down the temperature, your whole system is gonna be frozen. And then
I think yeah, probably we can discuss more later. But my point is I want to have some fluctuation, but not as large as the micro scale or nanoscale
okay, I
system.
see. Yeah.
Yeah.
So yeah.
Fluctuation is good.
Yeah, Tim, maybe I can describe more details with
Yeah.
you offline, because there is something you have to follow if you want your system still have fluid behavior. So there's a comparison between the energy level between the conservative force, potential force, and the fluctuation energy. If the fluctuation energy is too small compared to the conservative force, it's always is compared to two different force. If the fluctuation force, the fluctuation energy is too small, your system eventually will frozen. So you will have a solid system.
Yeah.
You do not have a fluid system.
Yeah. Also, sorry. Go ahead, please.
Go ahead.
Okay, yeah. So as I know, there's other kind of methodologies called the discrete element modeling, which is used to simulate the length scale, something like the particles with diameter larger than 10 microns. So in that case, the thermal fluctuations is negligible with respect to the, the mechanical vibrations. But also you can do something like a granular dynamics. It's something like it's something,
right?
Yeah. It's something similar to the Brownian dynamics, but with a larger length scale, which is called the granular dynamics, and it also considers the rotational motion of the particles. I think that kind of methodology may be another kind of choice.
Yeah, couple with CFD with the DEM is one option for larger system, or you can directly use SPH to do that.
Yeah, right. You are right. Yeah, SPH is also a good one. I mean, I think the thing is, depending on what particular problem you are interested in, you know, like DBD sometimes is very not efficient because first of all, say if you want to do like suspension, like dense suspension, you have to simulate the tons of solid, which does not really, I mean, play much role in terms of your system, but you have to simulate it because the DBD doesn't allow you to just simulate a dry system. Like I'm talking about dry means like all particle only system, right? So those like solvent-free method might be more suitable for what you may want to do, like for example DEM or others. Like.
Sure, thank you. Yeah, it's great discussion.
Yeah.
And then Xin, since you are an expert for both like DPD and lattice Boltzmann, so I'm just wondering, how do you compare the two different methods? Like lattice.
Okay. Yeah, that's a great topic to discuss. I view them quite different, to be honest. I view lattice Boltzmann as a CFD solver, even though it carries a lot of the microscopic characters, I would say, but I essentially consider it as a CFD solver, as a Navier-Stokes solver. It's a different way of solving Navier-Stokes, but effectively you are still solving the Navier-Stokes equation. So you know, that the, so I don't, sometimes, I mean, you probably see on my slides, I put lattice Boltzmann there, and I kind of, and a lot of people typically consider it to be a mesoscale or even microscale method, but like my viewpoint is like it's more CFD compared to like you know, DPD or Brownian or other particle based.
Got it. Thank you so much.
Yeah, no
I think
problem.
today we have quite a lot of good discussion here, and I think it's time for us to end today's like a seminar. But Teng, maybe you want to schedule other meeting with Xin?
Sure. Yeah. Thank you.
Yeah, feel free. Yeah, feel
Thank you,
free to
Xin.
send me an email if you want to chat offline.
Sure.
Yeah, and we really appreciate Dr. Xin Yung's effort and the time in providing such a great like presentation. And thank you very much. And we'll see you in the future, like CFSM seminars.
Yeah,
and,
yeah. See you guys soon. Hopefully, see you guys in person sometime.
Sure. Yeah. Okay, let's stop here and
Bye.
Bye.
see you next time. Bye now.
Bye.
Bye bye.